Off my priority list. Basically, beginning of 2014, I didn't really think about it again until November 1st of last year. November 1st last year, I was very hacked. I got hacked. The attackers had access to everything. They had my public phone number, multiple emails, they had all my hosting accounts, financial accounts, social media, like a dozen things. They actually had access to a copy of every email I've ever sent or received since I learned to read. So, to put it shortly, that was a very long week. In the aftermath, just about the only thing they didn't get actually is Bitcoin that I had in cold storage, which is when I dusted off this project. So this is Bitcoin is pretty cool because of some stuff that I'd like to show you now. So. By the way, you saw the link at the bottom here. If anybody's having trouble reading or anything, or especially online, I don't know how good the video quality is, you can just type in bitauth2017.com, and you'll see the presentation. It's the same thing. So this presentation is a website. I'm going to go ahead and switch the screen now. You can ask a neighbor. All right, so what I want to talk to you about is just shortly titled Bitauth2017, a reference spec implementation for a universal identity and authentication system based on Bitcoin. And in order to discuss this, I think I'm going to have to start with some of the primitives in Bitcoin. And about half the room kind of understood that Bitcoin has a built-in scripting language. It's really fascinating, really interesting, and it's actually quite simple. So I'm going to show you how it works. So we're going to learn how Bitcoin really works, how Bitcoin transactions are authenticated, which is where we start to get into the authentication stuff, and then how we can adapt that authentication for general use. Good stuff. So we're going to start with authenticating Bitcoin transactions. So the general assumption of how Bitcoin works is, you send Bitcoin to a Bitcoin address, put that in big quotes, and then the person with the private key can spend the money, right? So you public-private key cryptography. If you're not super familiar with it, if you have the private key, only you are able to create a signature associated with that public key. So it's a computer way of proving that you're the sole owner of a piece of information. So that's public-private key crypto. Interesting stuff. So this is kind of the high-level understanding of how Bitcoin works. Well, actually, when you send Bitcoin to a Bitcoin address, you're not. A lot of people assume it's like an account. It's actually you're sending Bitcoin to a little program. Addresses are programs. Addresses are encoded programs written in a scripting language that was built into Bitcoin from the day it was released, that we call Bitcoin script. So a more technical way to refer to the last slide is actually when you're sending Bitcoin, you're actually sending Bitcoin to what a lot of people will call a locking script. And in order to spend the Bitcoin, you need to be able to produce an unlocking script. So this is the most technically accurate way to describe what I just said a few minutes ago. This is exactly what you expect. And so I want to show you a couple examples of Bitcoin transactions so you can kind of get an idea of what I mean. Usually we talk about, there's a Bitcoin address and then there's a private key for the Bitcoin address. Well, that kind of transaction is called a pay-to-public key hash transaction. It's a pay-to-public key hash script. So that looks a little bit like this. There's a locking script and an unlocking script. So the locking script is the address. If we take this, we take the string that you see up here. There's I got a laser. Right, so you see op dupe, op hash 160, pub key hash, which is like a variable, op equal verify, and op check sig. That probably looks kind of scary and stuff. I promise it's actually not. If I wrote it out in words, you'll see, and I'm going to show you, I'm going to step through it in the next slide so you'll actually understand it. But it's basically, if you're familiar with any assembler code or assembly, Bitcoin has its own built-in assembly language. These operations all have a very specific action that they perform on a stack-based programming language, which is the programming language that Bitcoin authentication is programmed in. So so we've seen this, and you're just going to kind of get that in your head a little bit. You're going to see it on the next slide. So what we do to evaluate this, of course, when you create your address, op dupe, op hash, these things all are, you encode them basically on the computer, they're encoded basically to binary. And then when you take that and do some stuff to it, you can turn it into a Bitcoin address, which is what we usually see as how you send and receive Bitcoin. So in order to spend from a Bitcoin address, from a locking script that is a pay-to-public key hash address, you need to produce an unlocking script. Your Bitcoin wallet will produce this for you. You don't really have to know how this works, obviously. But this is what it's actually doing. It's producing a signature, and then it's showing the network what the actual public key was that was behind that original public key hash. So I'm going to show you how that looks. This is a full snapshot of exactly what's happening at every step in the program execution. We're going to walk through it real quick. So over here, I have basically, you see at the top I've got unlocking plus locking script. So what we do to execute this script is we take the unlocking script, which was produced by your wallet, and we put it at the beginning, and then we take the locking script, which was generated originally, it's like on the Bitcoin blockchain, it's got money in it, and we stick it after it, and then we start the execution on the left and go right, basically. If you're curious on how exactly this works, definitely check out the Bitcoin wiki on script. But I'm simplifying it a little bit. So we're going to start, and you'll see, so I put sig, pubkey, opdupe, ophash, this stuff, all that. It's down the left here. Got that? Right. So we start with sig, top left, sig, pubkey, opdupe, exactly. So sig at the top left. I have delineated in this, and it's common to do this when you're looking at Bitcoin scripting language. You usually use a less than and a greater than sign around variables, basically. So there's not actually a sig operation. It's literally the signature is what I mean there. And there's literally a pub key and a pub key hash. We'll get to those in a second. So anyways, going to get started. Sig. We're going to push a signature operation onto the stack. If anything that's in those brackets is being pushed, we're going to push a pub key onto the stack. That's the public key for the private key that controls the address. And then we run the opdupe operation, which takes the first item on the stack and copies it. So we've got two pub keys on the stack, and then the sig, right? Then we have ophash 160. Hash 160 is two hashing algorithms together, SHA-256 and RipeMD 160. If you're curious, Bitcoin wiki. Basically, hash 160 is just kind of a hashing function that most people in the Bitcoin world believe is very secure. So we're taking now ophash 160 takes the first value on the stack and gets the hash of it. And that hash happens to be, in the case of a valid transaction, it should be the same hash that will be calculated that was in the original locking script. Right? Makes sense? So now we're going to push the original locking script's pub key hash on the stack, and then we run an operation called op equal verify. It takes the first two things on the stack, the top two items on the stack, and it compares them. And if they are equal, then it throws them away and continues execution. If they're not equal, then it throws its hands up in the air and it's invalid. And then we've finally, so now our stack says pub key and sig. So what we've just done, the scripting language has just compared the signature and the public key that I have against the locking script stuff. And we've confirmed that we're dealing with the right public key. So now we've got two things on the stack. We've got the public key and the signature, which are over here. And now all we're going to do is check the signature. Right? So first we checked in the scripting language. The scripting language defined, first you need to check that this is the right hash. And once it checked that this is the right hash, it checked that the signature is accurate. Right? So op check sig, public key sig, and if it's valid, it returns 1, which is success. If it's invalid, it returns 0, which fails. So this is a valid transaction, it returned 1. So this would actually work. So if I had sent, 1 Bitcoin to an address that had opdupe this stuff, and you created a transaction where you're spending that Bitcoin to wherever you want, you're sending it to a new locking script, this would be a valid transaction. The transaction would be relayed, it would be accepted by a miner, and it would be mined by the network. Any questions about that? I know that it seems kind of complicated, but once you've seen it a couple times, you'll find it's by far the simplest kind of programming you can do. This is like lowest level programming. And to note, we'll get into some of the details of why it's designed this way, but you'll note that this doesn't take a very complicated processor or special instructions or anything like that to execute. This can be done on very low-powered devices, which is part of the original design of Bitcoin. Question?
Yeah, where does the private key come in?
Private key, yes. So you have the private key on your device. So in order to produce, I probably glossed over that a little bit. In order to even get this unlocking script, to even provide that to the world, you need to have the private key so that you can, first you're going to get the public key from it, which is just a mathematical function. One is the private key is a big number, and the public key is another big number, and they're mathematically related. Google it. So the public key is derived from the private key. And given the public key, anyone in the world can take the public key and the signature that you generated, which is also an interesting thing if you want to look into how it's done. I won't even attempt to describe it. That only the person with the private key is able to produce a signature that then mathematically anyone in the world can know definitively if this signature matches this pub key. Right, so when you've created your new Bitcoin transaction, we can just chop off that input part and we can kind of send it somewhere else. Somebody can kind of pull that apart and see there's a signature and a public key here. You can see that they're directly related. The public key, the signature must have been generated by the private key associated with that public key. So and that's all the public-private crypto stuff. But that is the unlocking script. So in order to produce this unlocking script, you will have to have the private key. Assuming we don't have quantum computing. So anyways, well actually, and one of the reasons that this is, the locking script has a hash is to be quantum secure. So this is actually an upgrade of one of the original Bitcoin transaction types, which was not quantum secure. So most of the network uses this one now in preparation for that doomsday. Good stuff. So any other questions about that? I think we've got
one more, sorry.
Yeah, no, please. Awesome.
The pub key hash, when you push that onto the stack,
yes.
Is that the same pub key hash that's generated from the hash 160, or is that coming from somewhere else?
Great question, yeah. So basically, I've put these all in a line, and so to verify this script, you can see these two items are from the unlocking script, and these items are all from the locking script. So of course, you have to have the whole transaction and some information from the blockchain to verify it. But it's probably a little bit harder to see it conceptually because I'm showing it as variables. So I'm basically I'm saying that this pub key is actually equal to the one that's produced, or rather, I'm saying that I'm trying to tell you that this public key is actually equal to this one that was produced by this function. But if it was an invalid transaction, then that public key hash would not actually match the one that was provided. These two public key hashes, this would be like public key hash 1 and public key hash 2. In fact, if I was going to fix this slide, I would probably do that because that would make it look clearer.
Yeah, because I thought they were the same. I thought the one you pushed onto it was the one you just generated.
Yeah. So. And every time I look at this, it always takes me like 3 minutes to realize that I'm thinking that wrong. So yeah, you're totally right. I need to fix that. Thank you. So these two public key hashes. Is that it? No, okay, cool. These two public key hashes are not necessarily the same, right? If it's an invalid transaction, it's because you signed it with a public key hash that doesn't match the one that's locking script, right? I can sign a random public key, whatever, that isn't related to Satoshi coins, and it won't let me spend it, right? So so these two public keys, they might not be the same, but we've just checked them, and the script interpreter confirmed that they are the same, and so now we just check the signature with opcheck_sig, and we get a 1. So it's valid. Good stuff. Awesome. So you guys are like already in the upper 1% echelon of people who understand Bitcoin now. Yeah.
A quick question. So no matter what the addresses are, so everybody is running the same version?
Yes, that is actually, so what he asked was, no matter what the addresses are, everyone is running the same version of this scripting language, right?
Right.
Yes, that's one of the things that I'll show you in a couple minutes why that's so important. But that's probably one of the coolest innovations about Bitcoin, actually. It's the first example of a perfectly compatible implementation that works all around the world. And it's guaranteed perfectly compatible because if it wasn't perfectly compatible, then it wouldn't get mined. So the miners are the ones who ultimately decide what the consensus is. So that is one of the kind of the underpinnings of Bitcoin that doesn't get talked about a lot, but the Bitcoin blockchain is a consensus mechanism. It is like a 2.0 version of a standards body. It's a much more efficient version of a standards body. for this language.
Isn't the scripting version now?
There is that's probably, and I'm probably not even the best to discuss it, but yeah, there's a proposed soft fork right now which would add versioning basically to the scripting language, which actually I'm going to get to a slide in a couple seconds that'll describe some cool stuff that could be possible with it too. Yeah.
There must be a block down the line somewhere that prevents me from releasing the cryptocurrency intended for something and then immediately releasing it again to get payment for something else. In other words,
Yes.
fraud, double, using the same currency.
Yeah, it's double spending. Yeah, and that's
the first one that gets into my block.
Yep, we call that the double spend problem, and that is the innovation that the blockchain provides.
The first block does that?
No, the first one that reaches a mind block, it may not necessarily be the first one that's
Yeah.
so if you get stuck in the mempool, that's a good way to push it.
Yeah. And ultimately, the way that we decide who owns the money is who ends up with the money on the Bitcoin blockchain. On the Bitcoin blockchain, no two addresses will ever get the same funds because it would make the block invalid. The miners enforce the double spend. So that is the innovation that Bitcoin brings to the digital currency world. That it is impossible to double spend with Bitcoin system because of the blockchain.
So you said the miners are the ones who control.
The miners, in order to validate every transaction, when people talk about miners, the ones who validate the transactions, and Bitcoin mining is we reward them with the newly mined Bitcoin. When we say mining Bitcoin, mining transactions, what we actually mean is they are taking the locking scripts from the inputs that are coming in, and they're taking the outputs. They're taking the unlocking scripts that are in the new transactions, and they're putting them next to each other and running the script on every single transaction that comes through the network. And if it's valid, they stick it in the block and take the mining fees. So this is what the miners are actually doing. In addition to when they put it all in the block, then they're trying to guess randomly until they get a block that has enough zeros. But I'll leave that for Bitcoin. Yeah.
So my question is, isn't that more of like a relay node versus like a pure miner? Because when I think of a miner, I think of some dumb server in a farm in China that isn't doing that validation.
Yeah. I'm generalizing a little bit. When I say miner, what I'm actually talking about is a mining pool. Usually the pool is the one doing the validating. The miners are dumb machines that are they're just chips that are plugged into a wall basically, and they listen to a trusted pool. But the pool is the one who is validating these transactions because they have a lot of money on the line. If they try to make a block with a transaction that's invalid, their block will be thrown away by the rest of the network because they won't agree on that. They will not agree that the miner executed the scripting language properly.
Can I ask you a question that's a little bit more on topic with what you just said? In the olden days, it used to be that the transactions were given a priority number, and now it seems like the mining pools, at least the ones I do, we base the prioritization based on fees to build our blocks.
Yeah.
And what happens, why is that priority number still there if you go to block trail or something? You can still see the priority number.
The sequence number for the outputs?
The priority number.
Let's talk afterwards.
Okay.
I'm probably not going to answer that question properly.
I'm just curious.
I'm not sure if I understand exactly.
Why it does.
Yeah, and I don't want to mislead you, so let's talk afterwards. Yes.
Just one more.
Yeah. This is awesome. This is fantastic because this is going to be really important for the rest of the presentation.
What's currently the length of the keys that is used in the new version?
Length of the keys. On a technical level, the length of private keys. Yeah.
But it's truncated, right?
Yeah. Usually, for most wallets, it's actually going to be 128 bits of entropy. Now, the private key itself is 256 bits. I'll have to refer you rest to the rest of the Bitcoin wiki because these are now detailed questions. But yeah, and I usually don't trust myself until I check the specs. But thank you, Chris. Okay, good with that. I'm going to show you now one more of these, so you're completely aware of the kind of power we're looking at here. This is a pay-to-script hash transaction, and it's on a specific template. It's a multi-sig pay-to-script hash template, pay-to-script hash transaction. So the locking script for a pay to script hash transaction is op hash 160, the redeem script hash, and op equal. I'm going to blow through these a little bit because they're going to make way more sense on the next page. But just so you can see, we've got a locking script, we got a redeem script, this is kind of interesting, and we've got an unlocking script. So the basic idea here is that you're actually sending money to the hash of a script. So most Bitcoin addresses are scripts themselves. In this case, you're actually sending money to the hash of a script. So you don't have to show the rest of the network what the authentication requirements you want to use. You don't have to show them what those requirements are until you're ready to spend the money, which provides, in the case of multi-signature transactions, yet again, quantum resistance and a number of other valuable things.
That's a big point, though, is you have to redeem it in the order that you have.
Yeah. You'll see that in the next slide. So what he's getting at is, let's do it. So I've gone ahead and put it up here. This is actually way simpler than it seems initially. We're gonna do it. So at the top here, this is pretty important. There's a 0 at the top left. I'm going to show you how that's relevant in a moment because it goes back to the scripting language standardization question that we had a minute ago. So anyways, we're pushing the value 0 to the top of the stack. Right? So we move down 1. We push a signature. I'm calling it signature A because it's signature for a key that we're just going to call A. We push a signature C to the stack. Then we're pushing the redeem script, the actual contents of the redeem script. So you hashed it and you created the address by taking a hash of the script. Now you're going to show the entire world what that script actually was, and you're putting it as part of your transaction. So you put that redeem script in there, and now we run that same op hash 160 you saw a few minutes ago, and we're actually taking the hash of that redeem script. So we're doing the exact same thing we did a minute ago. We're taking the hash of something and checking to see if it matches the one that was in the locking script. So yes, we're pushing the one that was in the locking script onto the stack, and this is kind of fascinating that we are executing a set of authentication requirements that are defined by a scripting language, which is on a high level really, really cool. So this is not something that's like programmed into Bitcoin, like the whole public-private key, all of that stuff, all of how you spend and use Bitcoin is actually not in Bitcoin. It's in scripting languages that your wallets are creating, and they're being executed by miners. So this is, in my opinion, a fantastically new and interesting idea. But here we go. So we're pushing this redeem script. That's from the locking script. And now we're going to check it again. Op equal. We check the top 2 values on the stack. And there again, it would have helped if I had said it was redeem script 1 and redeem script 2. I will do that in future presentations. And I'm going to tell you that they were the same. So op equal, took them off the stack and threw them away. Now we're through that. We know that we're looking at the right keys, right? Or rather the right script. So we're now validating against the right script. So now we've got the rest of this stuff to execute. So we've just done this op equal. Now we're going to push a 2 onto the stack, and we're going to push the public key of the private key A, and the public key of private key B, and the public key of private key C, and then we're going to push the number 3 onto the stack. So we didn't do anything over there. We're just pushing stuff onto the stack. Now we're going to run an operation called op check multisig. And this is one of the kind of hallmarks of Bitcoin security right now. This is really, really awesome, and other systems just don't have this, by and large. There are weird, complicated protocols to do something similar, but nothing as clean and beautiful as how Bitcoin does it, in my opinion. So we have op check multisig. What it's going to do, it's going to grab the first number after the top number on the stack. That is the number of public keys that are part of the multisig transaction. So it's going to grab these first 3 keys, public C, B, and A. Then the next value it takes is another number, and it's the number of keys in that set that must sign in order for the transaction to be valid, right? And so, and as we were mentioning over here, it needs to be in the same order, but that's super detail. So it takes sig C and sig A, and of course it's doing that properly. And this goes back now to the last thing I'll say here. So op check multisig just checked, and public sig C and sig A are at least 2 of 3 public keys. So opcheck multisig is going to return a 1. So you notice the 0 at the end there, though, and this goes back to the question you were asking of who's executing this. One of the coolest innovations about Bitcoin is that the entire network is, and they're doing it in such lockstep that there's actually a bug in the original implementation of Bitcoin where opcheck multisig consumes 1 more value than expected. And it was totally an accident and definitely a bug. Everybody knows it's a bug, and there's a comment in the Bitcoin core code right now and every other implementation of Bitcoin saying, we know this is a bug, but we have to do it. So the Bitcoin scripting language is rock solid as far as a standard. There are bugs that are standard. So this is a standard bug. So I find it fascinating. So opcheck multisig is going to return a 1. It's going to consume that random value. You can put whatever you want there. Most people put a 0. And actually, I might be misleading you. Maybe it might be on its standard. I don't really know. But everybody puts a 0 there. Just do it. And it's going to return a 1, which is true. It would return a 0 if it failed. So you've now seen, in my opinion, the world's coolest authentication system. Are there any questions about how this works? Is that
Why
yes?
isn't there a sig beat?
Because opcheck multisig, we gave it a number, how many public keys we wanted to check against. We gave it the 3 public keys, and then we gave it another number, which is the minimum number. Really, it's the exact number of keys that must sign for the transaction to be valid. So opcheck multisig allows you to have, and we call it M of n. You can have M of n signatures, and currently standard on the network, you can have up to 15 of 15. So you can do some really crazy stuff, which leads really, really well into my next slide. This is fictitious, but this is if I was going to describe to you kind of the power that we see here, this is kind of funny. And people who are familiar with the script options here, this is most certainly not standard. I just typed this a few hours ago. But I would describe this as a pay to the operations department or board of directors or a supermajority. And I'll show you what that transaction would look a little bit like. And actually, I haven't executed this. I'm not exactly sure if I can use bool or in this way. I would need to dig into it, but you can get the gist. So don't go try this and lose a bunch of money doing it. Don't blame me, rather. So anyways, assuming that I did it right, basically 2 of 3 multisig at the top would be the C-suite in your company or whatever, right? So you've got your operations department or maybe your C-suite in your growing startup or company, and you're trying to secure your company's new $30 million round. You're keeping it in Bitcoin, true to form, and you have yes, you have two of 3. I think I might have put that backwards. No, I didn't. I'm not sure. So 2 of 3 opcheck multisig, or, and I'll leave it to you to provide the unlocking script for this. I didn't even bother. That's a exercise for the reader. And then, or a 3 of 5 of the board of directors, right? They can take a vote, and they can vote in crypto and put it on the blockchain, right? And then, or, you've got to have a fallback plan for, big natural disasters or something, right? If the plane the board of directors was in goes down, you don't want the $30 million. The company still needs to be able to liquidate in some way, right? So otherwise, the world just loses all of that. So here we've got a 13 of 20 operation check multisig. It's a super majority of 20, of maybe 20 important people in the company or department heads or whatever. This would be a fantastic way for a big company to manage their treasury. Right? This is an authentication script. This is a locking script. That would be a great place to stick a bunch of money for a big company. And I'll just note real quick, and this goes back to some of the specification stuff somebody mentioned a moment ago. I'm obligated to tell you this doesn't actually work right now because it's a 520 byte limit on pay-to-script hash transactions. It's a network relay thing, so it would just be very, very hard to get your money back. And depending on how you did it, you might not be able to get it back. Of note, somebody mentioned the SegWit thing earlier. There's another transaction type called pay-to-script hash, pay-to-witness script hash. I think I got that right. Which has a 3,600 byte network policy limit and 10,000 byte consensus limit. If anybody's familiar with that stuff. So
Besides a Bitcoin company, perhaps, are there any companies that are accepting Bitcoin and using multisig to secure their company account? Do you know of any? I'm just curious if this is actually being adopted realistically.
I don't know if I can. If I'm.
If you're privy to give
No, yeah, I'll have to get back to you on that.
Okay, all right, sure.
I would say the Bitcoin wallet Copay was designed for companies to store their funds. I guess you have to. There's like a thin line between what's a Bitcoin company and what's just somebody who's really into Bitcoin, right? There's a lot of companies that are naturally big into the Bitcoin space. You know, gold dealers, electronics dealers, VPNs, places that usually deal with way too much credit card fraud. They're the ones who tend to love Bitcoin because you don't get into that fraud. And it's hard to say whether or not those companies are Bitcoin companies or if they just promote it really hard. But yeah, so anyways, we're going to move on a little bit, and I'm just going to summarize kind of what we went over. So you guys have learned a ton about how Bitcoin works. You have a solid idea of how it actually works now. The Bitcoin scripting language is really interesting and fascinating in a number of ways. It's very flexible with some very well-chosen constraints. There are no loops. If you're familiar, there are no loops and no go-to statements. They actually have limited processing requirements. They have a fixed evaluation time. It's not possible to get into an infinite loop or otherwise create a malicious Bitcoin script. It's not possible to create a malicious Bitcoin script, basically, at least by the definition of the language and so far as we know. So we got to work on that implementation. But other than implementation bugs, Bitcoin script itself is designed to not be Turing complete, is the buzzword. So yeah, it's got a very simple implementation. Also, there are less than 200 operations. It's possible to implement it in practically any language in a reasonable amount of time. With a good development team, you can implement it in pretty much any language in about a week and get it pretty solid. And if you're looking for tests, you've got the world's greatest test vector available. It's the entire Bitcoin blockchain. You can run all 80 gigs through your little implementation and confirm that it works. There's also some fantastic tests that all of the other libraries put out. So there's a Node.js implementation, a Ruby, a Perl, Python, PHP. I've seen like Haskell, Rust. There's tons and tons of implementations of Bitcoin scripting language in tons of different languages. And that's partially due to Bitcoin scripting simple to implement and of course network-wide accepted. There's a very definitive, absolutely definitive correct answer to what the specification is for Bitcoin script. It's whatever gets accepted by the miners. So we have a definitive way of resolving disputes, so to speak, in that, which is what I believe to be one of the biggest innovations there. Also of note, it's self-contained. I showed you the entire program. It didn't have any network calls. It doesn't need to access any hardware. There are no additional inputs that come into the script. When you have the unlocking script and the locking script, you can execute the whole thing and you know whether it returns a 1 or a 0. Right, so that itself is a really important piece. That means that you can give that unlocking script and that locking script to a basically potato computer, and it can execute it and it can get the right answer. Right, so you can literally run a breadboard with a potato and probably execute these scripts. Yes.
Did you say it is or is not Turing?
Is not.
Is not.
By design, yes. It is not Turing complete to avoid being able to create malicious scripts. And so it dramatically simplifies the security requirements for the entire system. The system you can just execute these scripts and you don't need to look at them or worry about if they're going to loop forever and heat up your machine and take it offline or whatever. Yeah, so it's designed to be able to be run by potato computers all over the world that barely have an internet connection, right? So those are some of the fundamentals here. So Bitcoin has, in my opinion, a really innovative authentication mechanism built in, and I think it probably doesn't get enough credit for what I see as being a very original idea that Bitcoin brings to the table. So the next part of this discussion, we'll discuss that a little bit more. So this is very interesting because Bitcoin's authentication system is very unique in a lot of ways. I would venture to guess there are very few, if any, other authentication systems that allow the user or the identity to define the authentication requirements that it uses, right? So if you log into a web service, the web service decides what your password requirements are and whether or not you can use two-factor and a bunch of other stuff. So they've got this big buffet of options, right? Well, so I'm gonna stamp those web services here. I'm gonna stamp them as static authentication. Ooh, bad. This is service-driven authentication, is what I would describe it as. And this is what I would contrast Bitcoin's kind of scriptable authentication to. Right now, most of the world uses what I would describe as static authentication. The service provides a whole bunch of authentication options. And real quick, as we're going through this slide, as a kind of a mental model, this applies to web services just as much as it applies to protocols like Bitauth and things like that. But for simplicity, just think about Facebook. This is just consider we're talking about like a service similar to Facebook. So the service, like Facebook, provides a bunch of authentication options. This big selection of authentication options. They start with the username and password, and they collect a bunch of information from the user in order to administer their static authentication system. So they collect a password, and then they get your phone number, they get your email. They get your secret questions. They get your physical address. They get pictures of your friends, right? So if you log into Facebook from a different IP address and they think that your password has been stolen, they've built this big system they've got basically a risk analysis system going in the background where usually if you get the right password, it logs in. But Facebook is a big company; they have to have a lot better security than that. And if you could just log in with your password, like everybody's Facebook accounts would be getting hacked all the time. Facebook has to cater to literally the entire population, right? So everybody on there is using the password one, or password with an @ sign. If I was familiar with recent events, so they've got a bunch of authentication options. You've got a username and password. You log in, and they've got they can send you an email with a button that you click to log in. And all of those. Well, we'll get to that in a second. So to log in, they issue a challenge. They issue one or more challenges, or otherwise challenge the user, prove who they are. And then when they verify the user response, you can come in. Right? Make sense? Good stuff. So I would say that this is problems all the way down. The issues here are that some user identities obviously have higher security requirements than others, right? You've got the average individual versus Microsoft's Twitter account, right?
Donald Trump.
I saw that. Yeah, like my Twitter account versus Donald Trump's Twitter account, right? Mine's probably not nearly as valuable. And if you can get Donald Trump's Twitter account, you can probably tweet something with some malware or something, and it can be it can steal a bunch of Bitcoin wallets and take a bunch of money. Might steal some financial account information. Like it's a big deal to keep important identities in various services secure. Just because on a high level. Those identities have big reputational risks, all sorts of other things. So on a high level, these services have to provide a big variety of options in order to satisfy all of those authentication requirements for various identities, right? If that makes sense. So the average user logging in to Facebook probably doesn't have the same kind of operational security requirements as a company's account on Facebook. And if Facebook has to build this big giant system with tons of band-aids and all sorts of other stuff, there's all sorts of risk analysis, and they're checking the IP address when you come in. If they're not sure, they'll show you some pictures from your friends, and you have to tell Facebook who they are and stuff. I mean, it's just all sorts of things that they've developed around this kind of static authentication system, right? And so obviously there are lots of inconsistencies across services, tons and tons of reinvented wheels. Basically, every service, when you start building a software as a service or a web service or something like that, you're working on your MVP, you're trying to get it out there, and you're like, oh yeah, we got to do authentication. Forgot about that. You just had a username and password for a little while, and then you got to figure out the password reset stuff. And then if you are letting users reset their passwords, who are you sending the emails through, and are their email inboxes actually secure? Are they secure enough for your service? And a lot of services basically just have to go, basically, if they can't keep their email secure, their account's gone, and we're done. And that is pretty much how a lot of services treat security, even today. So I mean, Twitter being a good example. The best authentication mechanisms that Twitter at least has publicly. I don't know if they've got anything special for super MVPs on Twitter or whatever. But the best you can get right now is two-factor. You can scan the QR code and you've got a number you have to type in after you type in your password, right? And that is fundamentally, if you're not very tech savvy, you're very, very phishable. People can set up a fake version of Twitter, get you to type in your password. You go in and you type in your two-factor, right? And that is a super common scam that happens all the time, and it's a big issue for a lot of these companies. So these companies actually have to also be monitoring domain name registrations. They have to monitor domain name registrations that look like Twitter. So if you can get a domain name that says Twitter and it has like 3 T's, then you could trick a whole bunch of people into typing in their passwords on your website, right? And this is just a constant problem for these companies. So they've got big divisions of security people set up looking for, is anybody setting up a new phishing scheme to trick all of our users? Because our users just straight up don't get this stuff. Yes?
What about BitID?
I will get there actually in a moment. This is actually a fantastic introduction. Yes. That's getting there in just a second. Right, so ever-increasing complexity. I'll wrap this one up, I guess. All of these systems, as your company, when you roll out your service, you have username and password authentication to begin with, right? And then you add two-factor because it's socially responsible or whatever. and now you get emails all the time to your security at whatevermycompanyis.com email address, and they talk to you about how you've got cross-site scripting vulnerabilities and all this stuff. It's literally just, and so you get the first obligatory emails from the various white hat security testers who tell you that you need CSRF tokens, and then they tell you that the emails that you're sending out are being not being authenticated with domain keys properly, and then you find out that somebody's registered a new domain that looks a lot like yours, and they actually bought an SSL cert for it. They're getting your users' passwords. This mess, the problems go all the way to the bottom, right? So and it doesn't get better as you become bigger. As a bigger company, it gets worse and worse and worse, and so you're just pouring money into this problem. I would contrast that to Bitcoin system, which I would just vaguely describe as scriptable authentication. If we were going to define a standard that looked like this. And I'm just gonna. So this is kind of like the spitballing. We'll look at how we would define a standard that works kind of like how Bitcoin works, right? So I would say the user chooses the authentication requirements on a very high level. The user picks how you authenticate the user. Then the service collects the user's locking script, right? Just like a Bitcoin transaction. And to log in, the user just provides an unlocking script. They execute it, and it's either a 1 or a 0. That's it. That would be really, really fantastic. We can make it that simple, right? So, if we were able to do that, here are some of the reasons we might want to approach it from that direction, and I'll show you some of the technical standards on how we can do that. So, why would we want to use scriptable authentication? Well, we hit a lot of them when I was showing you what I just terribly branded as static authentication, right? We're aligning the security incentives. Right now, to kind of put it into perspective, if you're looking to pay for a service, if you're looking to sign up with a new social media service or something like that, you got your new company, and you're trying to sign up with a social media service, and they're going to help you do like Twitter advertising or something like that. There are probably like 3-4 companies that are kind of the big dogs in that space, and they're the ones who are the top competitors in that space, and you're comparing those companies. As a consumer, you are totally not comparing those companies on their authentication requirements. They have almost no incentive to make sure that their authentication requirements are good. The only incentive they have is it would look really, really bad if all the accounts were hacked at the same time, right? If they can make it look like it was your fault, it doesn't even matter, right? So the incentives are totally wrong there. Whereas obviously they want to be able to make money as much as possible, but those companies they really shouldn't have to do all that stuff. It's their market, their product is designed to help you with your Twitter advertising, right? They're not security experts. They don't claim to be security experts. They just want to have a username and password and have it work. But then, of course, there's tons of other people who know all the different ways that people usually mess up when they're implementing username and password systems and password reset and CSRF tokens, DKIM, and all that stuff. There's plenty of people who are familiar with all of the kinds of common security problems that services tend to mess up on. And everyone does it. There are very few companies that start out from day one and implement everything perfectly. And when you mess up usually pretty bad. Usually looks pretty bad. But I would argue the problem there is the incentives are just totally wrong. That those services have no reason to be working on innovating in security authentication, like authentication security. Right, so if we're able to define a scriptable authentication system, it would allow us to push all of that stack, to push that entire ecosystem out of kind of the back office, so to speak, of startups that are working on another product and they don't want to work on this other product. They're working on their selling Twitter advertising. We can improve the user experience by moving the authentication stuff to the consumer sphere. So if the consumer is ultimately responsible for defining their scriptable authentication stuff, in the outset, it's going to be hardcore nerds who are doing it, obviously, like Bitcoin. But it means that the market moves away from those back offices of the companies and into Chrome and Firefox and those browsers and OS packages, and eventually into a different ecosystem of companies that are built to provide good user experiences for authentication systems. And in a sense, OAuth has kind of done this a little bit. OAuth has done a little bit better with this, but it's kind of funny because OAuth is like this. It's almost like a wart on Facebook and Twitter and all these other companies that they've had to spend so much money developing their authentication security that it was crazy for them to not package it up and give it to other people. Right? They wanted to monetize all of that dumped money somehow. Right? And that's how we got OAuth. Right? They've got all this work they put into it, and now they want to get at least something out of it, other than just not looking bad. Right? So kicking this out of the startups and giving it to its own market, by technical standard, by providing a way for those companies to start innovating on that, we get a whole lot more competition in that sphere. So we push it to the consumer sphere. So that also, by the way, if you're building your MVP for a company, you get to simplify your development requirements significantly. Right? When you're building your MVP, you do not want to be working about usernames and passwords and how you get the password, all the stuff I was talking about. Right? It's hard, it's complicated, you're going to mess up, and you're going to waste a lot of time and money on it. If you're building an MVP, this would be fantastic. If all you needed to do was, if you're using Node.js, you just stick in like a little middleware that's Passport Bitcoin, Passport Bitauth, I'll show you in a second, that verifies, takes their locking script, takes the unlocking script they sent you, verifies it, it's either a 1 or a 0. If they messed up, that's the problem of the security or authentication software that they are using. And that's going to end up being Chrome for a little while, and maybe Chrome extensions, and eventually develop into like ecosystem of sorts. Right. So, and to kind of wrap it up, fewer systems, fewer attack surfaces. So that we discussed with all of those systems, and especially if you're transitioning from being a little company to being like a mid-sized company, that's where the real rut in the road is. You're gonna mess up a couple times, and you basically today you basically have to hope that you don't mess up too bad. Like if you lose everything, you're done, right? Which I guess I'm thinking more from the perspective of a company that's using Bitcoin. Historically that was a little bit less of a problem, but now if you keep your money in Bitcoin or you keep your customers' funds in hot wallets or something like that, if you mess up, you're done, and that's happened to maybe 12 companies in the space so far. So very relevant to our space, right? So. Scriptable authentication and the blockchain. And via the questions earlier, we actually addressed a lot of stuff here, so I'm going to go ahead and hit it. So why would we use Bitcoin script? I think you kind of got the idea when I showed you that extra 0 at the end of the operation check multisig. Bitcoin script is ridiculously standardized to such an extent that everyone in the world can know immediately whether or not a certain type of script is valid, right? All you need to do is create a transaction that looks like it and broadcast it. If it gets in a block, you're good. And if you're not quite sure, wait for 10 blocks or wait for 20 blocks or something like that. If the network says it's good, you're good. So we've
Wasn't
got
like 6 blocks the longest ever that they
Yeah,
were
yeah,
able
so,
to find one.
yeah,
So
yeah.
6 for sure we did.
yeah, 6 is the number in the, I believe in the Satoshi white paper that is recommended for guaranteed basically. It's been very few times when it's ever been exceeded. But yeah, so and I mean consider just for a moment. We have Bitcoin has like a built-in standards body that you can send a little message to, and they will get back to you in an hour, right? So you can send a Bitcoin script to the blockchain, and if it gets in, you've got the answer within an hour. Like try to get that from any other standards body. It's like bar none. This is a fantastic customer service, right? So Bitcoin scripts. So I'll go ahead. So if we were going to create our own scripting language that allowed us to do this authentication stuff, it would take us quite a while, right? We got to create, draft specification creation. We got standardization management. Probably got to set up a foundation or whatever, and have a bunch of meetings. And eventually, we get some consensus and we get some standards acceptance. A bunch of people will exchange emails for like 4 years, and then eventually they'll have some rollout plan. It'll get delayed a couple more years. Then eventually, when it gets out, you've got to deal with backwards compatibility, right? And so what happens if you try to define an authentication scripting language just from scratch, pretend like we didn't know all this stuff about Bitcoin already. If you're going to try to do this, this would be insane. It's like, no way you're going to get every single company in the world to implement the same scripting language and have it be valid across ecosystems, right? You're going to have a lot of trouble getting all of the companies handling authentication security speaking the same language as all of the companies that are just consuming it, right? Well, Bitcoin and the Bitcoin blockchain, more specifically, fixes that perfectly for us. We are done. This is done. I guess, and moreover, anything you want to do with authentication, if you wanted to build a scripting language for authentication, for web services, a protocol, something like that, I would postulate that anything you want to do that's not available in Bitcoin script, you probably want to make available in Bitcoin script because we probably want it to. So they are the same market, so much so, and I'll actually dig into a little bit more, that I would say that the language specifications should match exactly. The way that you want to authenticate Bitcoin transactions is of course, the most secure thing anywhere, right? It's money. You want to authenticate it as securely as we can, as our human brains can come up with so far. And I'd say it would be not unreasonable to say that there are some applications for web services in which big companies would want to do the same. Is there a question?
Yeah. Just trying to understand, because we're talking about the security and authentication. How did the $75 million get stolen?
For which one? Mt. Gox?
Repeat the question.
Oh, yeah. You're asking how did the 75 million get stolen?
How did the $75 million get?
What is it? Bitfinex? Oh, yeah. Well, in a funny way, I mean, I don't want to speak directly to. Well, I would say that the problem was the static authentication security.
That's why I'm just.
Oh, yeah. I would say the problem was actually a static authentication system. A static authentication system set up between two companies failed epically, and a bunch of money was stolen. So, that's basically the security that was going back and forth between those companies failed.
No, the keys were compromised. They were holding.
They literally got the keys. Yes. Yeah. Yet another static authentication system failing at it. Yeah. Right. So, anyways, why would we use? So, I'm going to now show you a technical standard that I would say is a way forward for the Bitcoin ecosystem and more generally the rest of the authentication world that uses the Bitcoin blockchain to track identities. And why would we use the Bitcoin blockchain to track identities, right? So I think I've described to you why the Bitcoin scripting language is absolutely, bar none, 100% exactly what we want, and nothing more, nothing less. It's actually designed to be exactly what we want because Bitcoin authentication, same thing. I would say that the Bitcoin blockchain is actually specifically designed to secure identities, right? If you look at the contents of the Bitcoin blockchain, we've just discussed that when you send Bitcoin to an address, you're sending Bitcoin to a locking script. when you create a new transaction, you're sending Bitcoin, you're unlocking that Bitcoin and sending it to a new locking script. The Bitcoin blockchain is one giant secure directory already of identities and their authentication requirements. Right? You can send Bitcoin to a different identity, and it's got authentication requirements coded right there. The Bitcoin blockchain is a secure directory already, and it's built to be just this, a secure directory of identities and their authentication requirements. And in addition, the Bitcoin blockchain also provides tamper-proofing, which is a secure thing, and censorship resistance. So there's maybe a case to be made that a system, well, I'll dig into it. There's probably a case to be made that you could develop a system if you didn't have the same requirements, censorship resistance and tamper-proofing, that you could do something slightly more efficient. But I would say it's probably very hard, and you're going to have some trouble. We've kind of when you step back and understand the Bitcoin blockchain as already a directory of identities and their authentication requirements, it becomes a little bit more intuitive as to how we would create generalized identities for use in authentication with web services, right? How do we create an identity on the blockchain? So this is where we get into the standard specification. There's a GitHub repo, if you're following along the presentation, it's at the end. But the Bitcoin improvement proposal, the white paper, is in there if you're curious. Here we go. What I would say is a Bitauth. So the spec that I'm going to discuss with you is Bitauth2017. It's just a reference implementation and a spec for how to do identities with the Bitcoin blockchain. So I'm now, from this point on, I'm just going to say Bitauth for Bitauth2017. I'm saying Bitauth2017 a little bit because it's a little bit of naming troubles between there's a blockchain ID, there's a bit ID, there's a Bitauth, there's a block ID, there's an auth coin, an auth base, there's like literally everything is already taken. So I think this is the best name for this, and I'm just going to use it. Bitauth2017, right? So I'm going to refer to it as Bitauth now, but it's Bitauth2017. If you Google it, that's what you'll find. Bitauth2017 identity is defined by an auth base. An auth base is a Bitcoin transaction. It looks like a normal Bitcoin transaction. It is a normal Bitcoin transaction. This is the simplest kind of auth base you can get. It is a simple transaction. It's got some inputs or whatever, and it's got one output. We call the output the identity and the signing output. We call it identity or signing output. All right, so there is nothing about this transaction that's unique or different. Literally every single Bitcoin transaction that has at least one spendable output could be an auth base. So in a sense, we're actually getting some censorship resistance there, which is kind of nice, plausible deniability, etc. Right, so this is the simplest kind of auth-based transaction. I'm going to describe to you how we build this up into deriving locking scripts and unlocking scripts and how to build it into services. So that's what I'm going to get to by the end of this presentation.
So do you have to spend Bitcoin to get the authentication?
In this scenario, yes, and I'll go over at the very end. Basically,
Bitcoin is publicly published on the blockchain.
Yeah. So in order to create an auth-based transaction, you're taking some Bitcoin and you're spending it to a new address. You're spending it to a new address where you have defined the authentication requirements you want to use.
So like a tiny fraction?
You can use just a tiny fraction, exactly. And actually, that gets really, really nicely into this slide. This is the most complicated auth-based transaction you can create. You've got funding inputs on the left here. You've got your Bitcoin from somewhere. It gets sent, and then you've got an identity output and a signing output and some other outputs. There again, there's nothing unique about this transaction. The only thing that makes this an auth-based transaction is that I'm calling it an auth-based transaction. Every single transaction on the blockchain that has at least one spendable output qualifies as a valid auth base. If you reference it, you can trace it and find the most recent locking script for it. So it's very, very easy to create identities. If you have a Bitcoin wallet, the Bitcoin wallet can implement this very simply by simply keeping the keys separated from the rest of the keys. Right, so funding inputs, we got an identity output and a signing output. And to your point, so to answer your question, would you need to send money there? You do need to send a little bit of money in order for it to be relayed by the network. So you need to send, in modern day, in US dollars, you need to send like a penny or something to each of them. No big deal. You might want to, we'll get into it, but you might even want to send, if you're a big company, you might want to send 10 Bitcoin to your signing output, and now it's a bounty, right? If anybody gets your signing keys, they can steal it, and now you know that somebody has your signing keys, you're good to go ahead and switch it over. It's a great way to know that you should revoke your keys, right? So this is a great way to tempt hackers into telling you that they hacked you.
Wow.
Anyways, we'll get to that. It's pretty cool. So this is a normal Bitcoin transaction. It's only different in that I'm calling it an auth base, right? So we have an auth base. To get an auth head, we're using the same terminology as Git and other graph systems. Fits very nicely. To get to migrate your auth base to the next stage of your identity, to revoke your keys, and to revoke your previous signing keys and issue new ones, you're going to create another transaction where you spend the identity output of your auth base. So if you created a transaction originally that you decided to tell the world was your auth base, you've got a transaction ID, which is the hash of the transaction. Anyone in the world can take that number, it's a big number, and paste it into Google, literally, and it'll show up on 10 Block Explorer websites. You can click on that, and surely, when we implement this stuff, those Block Explorers would then be able to show you what the latest identity is for this transaction, what the latest auth head is for this transaction. So before I go forward on the slide, just note, so the first output is the one that we mark as our identity output, and the second output is the one we mark as our signing output. This is the more complex form. We're keeping them separate because there's some cool stuff you can do here, right? Your identity output could be in cold storage, and your signing output could be like one of one, right? So if you get hacked, it's not deadly. You just move to a new set of signing keys, and your identity was never actually compromised. They just got your signing keys for a little while. So this is generally a cool system. So but the thing to note here is we're sending the identity output of our auth base to the next transaction, and it is we now call this the new auth head. And this is the most important piece here. So here's then what we can do. We can resolve the latest auth head given any transaction ID. So a Bitcoin transaction ID is, there's only there will be no collisions in Bitcoin transaction IDs. If ultimately, by the year 2050, we find collisions in SHA-256D, and then the Bitcoin system, surely, and Bitcoin script will have to handle that system. Already, Pay2Script hash has some nice stuff where there's a transaction witness ID and some other stuff. So, and the transaction malleability stuff, if you're familiar with that. The Bitcoin system is working pretty hard to make sure the transaction IDs are unique. So we can leverage that very nicely. We can take any auth base ID, any transaction ID that you define as your auth base, and we can resolve it to the latest auth head for a given identity. So here I'm showing a diagram of that says September 2017. You can't see it, and it says auth base. Right? If you just imagine, a company like Microsoft creates their identity in 2017, September 2017. They go through some management changes. They go through some operational security changes. The security team changes, and they decide to roll out a new authentication mechanism for themselves as a company. Right? They're doing that pay to operations department or board of directors or supermajority. They're doing some kind of crazy scheme like that, right? And they brought on a new guy, and then when their existing security guy left the company, went somewhere else. They need to revoke the keys. They just make a new Bitcoin transaction with a new signing output, which I'll show you how we use it, which creates a new set of authentication requirements with the new guy's keys and not the old guy's keys, right? So this is a good way for us we can immediately give them the Bitcoin blockchain, and you'll note, if anyone's familiar, this is also SPV validatable. So you can, if you're running an SPV wallet, or an SPV node, you can also trace to the Bitcoin blockchain to get the latest auth head for any given identity. So this allows us to take that hash, that identity that represents Microsoft in this case, and our wallet can follow it all the way through. So, May of 2020, I want to verify if I downloaded the right version of Microsoft software or whatever. And my operating system has had their auth base hash programmed in since 2017. But that's totally cool because Microsoft is able to control exactly the path that their identity has taken on the Bitcoin network in all that time. And here I'm showing another auth base, February 2018, a little startup got started and they got big and Microsoft acquired them and they decided to operate under the same identity. And so they just merged their auth base in another transaction in the future. If they just pay the identity output for their transaction, they can merge it right in. And if you resolve either the auth base here or the auth base here, of course you're going to get to the same auth head. So that's kind of well and good. Does that kind of make sense? Any questions about that?
So basically, when we have certification authorities that have certs,
Yeah.
states can control those.
Mhm.
Like in the system.
Yes.
This is exactly.
Yeah. So you're already seeing some of the implications here. This is pretty cool, right? So
Yeah, repeat for the audience.
yeah. So I'm going to repeat it in 2 slides.
Okay.
Yeah. So intuitively, you're starting to see the bigger picture here. Microsoft can sign their SSL certs with an auth base, which resolves to a new auth head that you can verify 10 years later. We might have upgraded the entire Bitcoin blockchain to stop using public-private key crypto, right? If quantum computing becomes tabletop, if you can buy a quantum computer for $1,000, the Bitcoin network is going to migrate to a new transaction signature system, and so is Microsoft. And their auth head will move on. Oops, their auth head will move on, and by May of 2020, or this might be 2040 or whatever, they've already migrated to a totally different script system, which is authenticated in a totally different way. But we can still, given that ID, which was programmed into our browser back in the year 2017, we can resolve all the way down to today's signing credentials. And the Bitcoin blockchain is a fantastic place to do that because, later, importantly, assume that all of the people that worked at Microsoft in 2018 here, all of them have left and joined some criminal syndicate, right? So year 2040, they have keys. They still have their keys from the year 2018. And they could still sign as Microsoft at the time. So if you have a static authentication system, which uses the certs that Microsoft had back in 2018, you're going to accept their signature as valid, right? Whereas if you use a scriptable authentication system with a migratable auth head, and you fundamentally take that as your security assumption, you are not vulnerable to a wide range of potential attacks that happen later, right? And that's, they don't even need to join a criminal syndicate, right? If quantum computing becomes tabletop and all their keys have been divulged, if everybody can see their keys on the network, we just reverse the keys really quickly, and you can sign an address just like they would. So anybody in the world will be able to easily sign Bitcoin transactions as they sign them today, because our computing has evolved, or our understanding of certain mathematical functions, things like that. So this is kind of future-proofing cryptographic systems. So to kind of tie this up, I mentioned that signing output earlier. So in that simplest version of the auth head, there's just one output. That's very easy. You might send most companies are probably not going to worry too much about spending $1,000 on this, right? So they'll send a Bitcoin, and they're probably not going to think about it very much. You could send like $1 or whatever. It wouldn't matter. But you have your auth head. We just saw how you resolve it. You just calculate all the way through the Bitcoin blockchain up to the latest one. And the latest auth head is the latest auth head, which has been confirmed in 6 Bitcoin blocks on the longest chain. There we go. So by saying it that way, I've just described absolutely definitively and with absolutely no ambiguity how this protocol works, which is a cool feature of Bitcoin. Anyways, signing output. So a Bitauth signature is when we take the signing output and we use that Bitcoin script we use the locking script of so the signing output includes the locking script. A Bitauth signature includes the unlocking script for that transaction. You can stick it next to the locking script and execute it. If it turns to 1, the signature is valid. And then all we do is include in that the whole thing which is signed, we include what we call a digest output. This is the message digest output for a number of reasons. I'll dig it. So this is a standard way of including a small bit of information in the Bitcoin network. You can provide an op return. This is provably unspendable. If you send money to this, everybody in the world can know immediately that it will never, ever be possible to spend it again. So you've burned that money in a way. And so here we just, we are using the same system by which you create Bitcoin transactions to create an invalid Bitcoin transaction, which we include a digest of the message we want to sign. And I'll step back real quick. This protocol, everything that I'm showing you here, is kind of the lowest level of this system. So the only thing we're concerned with here is connecting these off-base identities, resolving them to the latest identity, and then signing a message given that identity, right? That is the low level that we're talking about here. Higher level protocols can figure out how you do login authentication with this system. So we've provided a perfectly trustless system for which you can resolve the latest signing requirements and sign absolutely unambiguously as an identity. So this is the fundamental building block that you need to build a larger scriptable authentication system. So the only thing that this does is sign the hash of a message. I'm not sure if I hit it earlier, but the hash of a message, basically a hash is a mathematical function. You can give it anything and it will return just a string. It will return like a little bit of, basically a set of numbers. It will return a big number. And it's thought to be impossible to generate, to create a message which when you run through this mathematical function returns the same number as any other message. So a hashing algorithm is something that we can trust will return the same number every time you give the same message to it. And no other message will return that number. So hopefully, I think probably a lot of people probably have heard of hashes, but in case you haven't, that's the gist. And so our digest output is where we stick the digest. And we call, in cryptography, you usually will call the output of a hashing function, when you pass a message to a hashing function, it's usually called a message digest. So we stick the message digest in here, and we also stick the algorithm which we used. So in most cases, you're probably using like hash 160, which we saw earlier, or in the Bitcoin system, we have a hash 256, which does 2 rounds of SHA 256. Generally, this system is somewhat algorithm agnostic there. It does not matter what you stick in the digest output. And since it doesn't have to be broadcast to the Bitcoin network, it doesn't have any, really, you don't need to have requirements for limits here. In the protocol, we do define some limits because it's easier to implement, basically. But I'll leave it at what you're doing here is signing in an unambiguous way with the unlocking script that matches your identity. You're signing a message so that at any point in time in the future, they can grab this block of information. It ends up being binary, and give it to a program, and give that program your off-base identity. It can resolve. It can check on the Bitcoin blockchain, and then resolve relatively quickly whether or not you signed this message with your latest identity. And that is the entire gist of the system. That is the entire goal of the system. So, and we provide the algorithm in the message digest so that there's no ambiguity. If you sign a message that you say is with one hashing algorithm, but there's a vulnerability in another hashing algorithm, someone else can't create another message in that algorithm that equals the same digest and claim that you signed something you didn't. But yeah, this technical details, but of interest. That's why they're both there. So this is just a rock solid way of affirmatively identifying that the identity defined by that auth base, when we resolve it to the latest auth head, and we take that signing output, we can take that and validate it against this message and know with absolute certainty 1 or 0, true or false, either it was correct or not. And on top of this, it's possible to build a lot of other cool stuff. I'm going to get to those things in a second. I'll just note this real quick. If you're curious, and especially what you're talking about with the asserts and decentralized systems and things like that, a layer 2 protocol for this, a fantastic way to do that probably would be to create, I don't think when I was here I said, the only difference when we validate a Bitauth signature, we could more correctly call it a Bitauth signature transaction. It is a valid Bitcoin transaction, The only difference is it has one requirement that we have relaxed. It does not necessarily need to be properly funded. So you can spend your signing output to a new digest output that contains 21 million Bitcoin or whatever, right? And that's clearly not going to be accepted by the network. So that's a fantastic way to avoid your signing output being spent on the real network. So if you're wanting to, as I'll show you in a second, if you're wanting to use it for higher level things, then you don't want to send your message signing into Facebook and have it be broadcast to the network. Now you've spent money and a transaction fee and a bunch of stuff. Yeah. So this allows us to definitively make this an invalid transaction while still using all of Bitcoin's transaction authentication model. Right. So that is relevant here. So we can make a valid Bitauth signature transaction, which we can broadcast to the network, and that is when we spend the signing output to. And I'm talking about how you might build a layer 2 protocol on top of the system, which is only a layer 2 protocol that is decentralized in some way, right? So you can spend the signing output, and I just, as an example, called it an auth-head expansion transaction. And this might spend the signing output to a transaction that has a number of meaningful outputs. And I say that very, very generally. There are a bunch of things you could do, but suffice to say you can stamp information into the blockchain that's related to your identity, right? So some of those things, I just threw some on here. Most of them, once you kind of understand the system, there are a lot of things that are cool that people want to do with stuff. So obviously, decentralized DNS, you can stick an IPv6 address or an onion address in a meaningful output for the identity, and you can definitively tell the entire world exactly what the address is of your website at that moment. You can migrate it in an hour, so it's actually faster than the DNS system. If anybody's familiar with that. And then also like proofs of ownership, associating a document with an identity in the blockchain. Kind of standard stuff when people talk about the blockchain. Inter-wallet addressing systems where you can share your latest Bitcoin address basically. With all of the wallets out there. So if they have your Bitauth identity, if I scan your QR code, I get your Bitauth identity, I can resolve immediately what your latest Bitcoin address is. So that allows us to have some inter-wallet interactions and things like that that are pretty nifty. So those are pretty cool. But I'd like to, those are big things. Those are hard systems, big things that need to be implemented. Obviously, they're going to take a lot of work, and talking about it doesn't really help. But there are some things that are ecosystem-wide that are immediately viable, basically. And one of the first ones that we should discuss is user-friendly, secure software signatures. Right. So, has anybody in here ever downloaded Bitcoin Core? All right. So, how many of you got PGP and grabbed all of the developers' signatures and validated it? So, a few less hands. I see like 4. Excellent. All right. So clearly, there's this gap in security between what the Bitcoin Core developers are able to. They're providing fantastic proof that the binary is correct, but the users don't exactly use it properly. Most users are probably not validating it, and no one in here. But there are surely users that are not. What we can do is the Bitcoin Core team could decide that they want to create an identity in the system. They create a locking script that adequately describes the relationship that they have with the project. So you create a 10 of 10 address, a 10 of 10 multi-sig wallet or whatever, but maybe a fallback or whatever, or maybe no fallback. If one of them disappears, maybe they're worried that if one of them disappears, there's a state-sanctioned violence or something against them, and they want the identity to be burned. Right, so that's a viable security thing they need to be thinking about. That's something it's hard to define me sitting out here, but they're the perfect identity to define what their real-world risk and security requirements are. So they might decide to do a 10 of 10 where if one of them disappears, it's gone, and you need to get a new auth base from the new team. Right, so what they can do is they can use that auth head. They can use the auth head that's resolved from the identity, and they might migrate as many times as they want. Use the signing output on that. It's just like 10 of 10 or whatever, and sign a bitcoin.zip.bitauth or whatever, right? And you download it. You click on it. and a utility on your computer uses an SPV validating Bitcoin node to quite rapidly resolve the latest auth-ed, grab the signing output, and execute the script. And if it's valid, then you're good to go. And of course, you need the identity of the developers. But if you've downloaded the software before, or if you can go and check on a bunch of public websites or something, I mean, it'll be very, very obvious what their identity is. It's not very hard to just copy and paste that string on. It could be on their Facebook and their Twitter and a dozen other places. Once you've seen enough pieces of information, you can be reasonably sure that this is the right ID. There might be other certificate authorities, as you were mentioning, who might sign a big list of IDs that they're familiar with. Key value, this is ID, name of the entity, ID, name of the entity. This one is Microsoft, this one is Google, this one's Twitter, this one's the Bitcoin core team. So this is something that can be built into the operating system, built into end user products, anything like that. Users don't necessarily need to understand the whole validation system. Right? You just double click on it. If it's valid, then it pops out, and maybe it'll pop out. It wouldn't be bitcoin.zip; it would pop out as a folder, right? So from a user's perspective, your grandmother downloads it and clicks on it, and it opens up. And she doesn't necessarily realize that we've just validated it against probably like one of the most advanced authentication systems ever created, right? So that's pretty cool. So given that, now to put it in perspective a little bit, I'm going to talk about some real-world security problems that are like zero-day problems today. Has anybody ever built an Android app in here? All right. So have you guys deployed to the Android App Store? You remember when you signed the app? You signed the app with a key. And so basically, for everybody else, when you create an Android app, you build your app. You're all excited. You finished up your application. You're ready to give it to the world. You put it up on the Android App Store, and you start selling. You start getting big. You get a few other new employees or whatever. You start. One of the other guys is now signing the app for you, and now you're like working. You're doing the CEO thing, right? You got like 50 employees now, and now there's like 12 different guys who are working on the app. 3 of them are all of them are doing signing. Like 2 years later, one of them leaves, and he's joining another company, moving out of the country or something like that. That's when you realize that the key that you used to sign it that first day you put it in the Android App Store is the only key the app can ever have. All right. So and you probably didn't even realize it, but when you gave that key to all those other employees, you just made a bunch of loose ends. Right. So when you sign an update, it goes up to the Google Play Store, and Google's doing static authentication. Obviously, they're doing all sorts of risk analysis, all sorts of things to make sure that it's probably not malware. It's probably that you meant to do it, right? But then when the app appears on your Android device, ultimately your device checks to make sure it's signed with the same key that was used on the original day it downloaded it. And now you're in a scenario where you've got an employee or a former employee who may or may not have left in bad blood or something, right? You have no idea what the relationships are there. And there is a loose key out there that can sign as your company. They can distribute a rogue version of your app. If you're a Bitcoin wallet, if they can get the user to download your app, all the money is theirs, right? They can, and it's even worse in a lot of ways because they even have plausible deniability, right? There's like 12 different people that have the key. All the money disappears. Who do you blame? Right? So there are a few companies that are handling this, but very few are really. I shudder to think how many massive companies have like hundreds of people in control of that key. It is certainly not just the C-suite. I'll tell you that. So there's this zero-day problem, and that's just Android. Let's talk about iOS. So iOS is the same kind of deal. In some ways it's better, and in some ways it's worse. Android, Google has clearly the Android signing system was designed for a day that did not have Bitcoin. Bitcoin, if you steal Bitcoin, the Bitcoin is gone. It is irreversible. You can't go to the authorities and ask for it back and stuff. The Android signing system is not exactly, that whole static authentication system does not really treat Bitcoin as securely as it needs to treat it. But it does do some cool stuff, and they should be lauded. because they do disassociate themselves from the signing process. So Google cannot possibly give you a bad version of an app because it won't validate on your phone. So there are trade-offs to these two systems, and credit where credit is due. Google has done well with that, but there's still, in my opinion, probably a more relevant and immediate security problem of there are a bunch of employees who know a lot about your company, know a lot about your systems, and have the keys. However well they liked you before they left is how well your keys will be treated, right? Or I hope you gave them a good farewell package, right? Yes.
I just want to interject a worse problem is a lot of small companies outsource that.
God.
So it's like they hire somebody else to do it, and they don't even have a clue that there's this whole back end of the keys and everything.
Yeah. What was just mentioned for the video stream is that somebody mentioned that that a lot of companies outsource their Android app development. Yeah. Yes, and there's actually a study recently where there is actually a signing key that signs over 100,000 Android apps. So just so you guys get an idea, I have no idea how many people have that key. It's probably not a small number, and it's like, I mean, a huge part of the ecosystem is just signed by the same key, and everybody's like, that's probably okay. So yeah, but credit where credit is due. In a way, that system is designed to disassociate Google from being able to be, agents of a dictatorial regime can't walk into Google with guns and threaten to kill a bunch of people if they don't distribute this bad version of an app to a political dissident, right? That's ultimately the kinds of adversaries that these crypto systems are fighting. Apple. When you're in the Apple ecosystem, you trust Apple 100%, absolutely. The certificate system in Apple is you trust Apple 100%. So in some ways, in real terms, in a sense, it's more secure. So at least with a Bitcoin wallet, Bitcoin's like small enough. There's probably few enough people at Apple who could get around their internal security controls to distribute a bad version of the app. So in a way, there's probably a little bit less of a zero-day vulnerability there. There's probably some culpability, right? If an Apple person distributes a bad version of the app, they probably can tell who did it. So in a way, Apple's is probably significantly more secure as far as Bitcoin is concerned. But that's not to say much, right? It's still, you're trusting a solid 50 people with signing apps. And in a day and age when money is digital, that is going to be a very serious problem. So this is a tidal wave problem that we are moving towards probably in the next few years, and especially as the mainstream starts to get Bitcoin. If this does not get addressed, a bunch of people are going to lose their money all of a sudden, and they're not going to understand why. This is why. Right. So, by the way, if you have money in a wallet on one of these operating systems, it would be a good idea to use multi-signature, and don't trust the same. Don't trust two devices of the same ecosystem. Right. You can diversify your risk by having one key on Android and one key on Apple. Right. And then if a rogue employee takes it off an Android, and then it would be much harder for that employee to be in cahoots with the guy at Apple who can also sign, right? So multi-sig is a fantastic innovation for Bitcoin. You should be using it right now because there are big problems like this, and there are probably a dozen others that I have no idea about and I can't talk to you about. Like there are probably a dozen other big problems with the security assumptions of having Bitcoin on a phone or a computer or whatever. So multi-sig, fantastic. Right, so I said what happens when a signer leaves the company. That's a big, massive problem right now. Well, with the auth bases, I think I've already described, if you sign your identity with an auth base, we've solved all of those problems, right? Fundamentally, the app can check against the original version it downloaded, and it can see their identity there. If you trust a Bitcoin wallet, if you put a Bitcoin in your Android Bitcoin wallet from a certain vendor, you've basically you've told the universe that you trust that developer with one Bitcoin. Right, and that developer has an incentive to keep their identity updated, right? And when somebody leaves the company, they're going to migrate it the day after, right, or the day before, hopefully. And they're going to have their signing keys are always going to be as up to date as possible. And the good ones are going to have their identity keys are going to be offline and super secure. So if they have to pull the nuclear option, they get in the dark room with the C-suite and the board of directors, and they do that big giant multi-sig transaction to move the auth-head, right? So it's like there are ways of that allows us to start with this hash and resolve to the latest auth-head, grab the signing key, and validate the Android app the app update that we downloaded for Android or iOS is from the identity with whom we originally trusted the money. So we've closed that security gap. So this is a real world example that is in the wild right now, which needs this desperately, or something like that, obviously. Right. So I've got a couple more, two more that are relevant here, and these all build on each other. So this is actually the problem that originally got me working on this in 2013. How to have a good user experience for backing up Bitcoin wallet is basically the high level question. Now we just described how if every app on the Android ecosystem had an auth-based identity, there's some pretty cool stuff we can do now. So my dream world there would probably be, from a high level, it's a good idea to not share private keys between devices. When you share a private key, you're opening up that key to being vulnerable to a whole new stack, whole new set of, you start at the hardware, right? There's a bunch of compromises in the hardware. You get up to the firmware, a bunch of compromises there. Once you get to operating system and user land layers, you're going through massive amounts of potential security vulnerabilities, right? Copying a key to another stack of vulnerabilities is a terrible idea. Always has been and continues to be a terrible idea. There's still a lot of security systems that rely on doing that, which is mind-blowing. Yes?
I was going to ask, what are the alternatives? Sometimes we have to.
Fantastic, yes. Well, so Bitcoin is the first time we've had really solid... So what are the alternatives to copying a private key? Bitcoin is actually one of the first systems which has a fantastic alternative. It's multi-signature. You can have a private key that is randomly generated on that device. You never take it off the device. You have a private key randomly generated on this device. You never take it off the device. And they can communicate only the public keys and create a locking script. They can create a locking script for a Bitcoin address that requires both devices to sign in order for the transaction to be valid. And if we use this Bitauth system, the same can be true if you're logging into Facebook and whatever, right? So we can actually this allows us, multi-signature is fantastic because it allows you to diversify in terms of risk. It lets you diversify your risk across multiple vendors. Basically, all of them have to be compromised at the same time by the same entity for you to be compromised. So multi-signature is a fantastic alternative, and it solves the problem perfectly.
Is that so almost 2 years ago, I lost my computer in fire, which
Yeah.
in my treasure.
Yeah.
I was able to use the C words to recover. Is that multi-sig? C words?
Well, it depends. You can use, so the question is, the person in the back recovered a wallet that was lost in a fire using the 12 words for a Trezor wallet. Depending on how you were using it, if you were using it with a multi-signature wallet, so an HD wallet with a multi-sig setup, you would have two sets of 12 words that comprise the wallet. If you just have one set of 12 words, I'm willing to bet that it was probably single signature, which means that you're trusting that ecosystem. And Trezor is maybe not necessarily.
A real world example.
Yeah, definitely. Thank you. Yeah, Trezor is probably significantly better than just trusting it with one Android device or one iOS device. But still, I mean, a lot of people put a lot of trust in hardware wallets, and I find it concerning. I do not. Maybe I'm a little bit more paranoid than most, but there are definitely things that are hard to understand security vulnerabilities that are just hard. Yeah. Secure computing, I personally think, is, in the words of Peter Thiel, 20 years away. It means it's not ever going to happen. Secure computing is just, I have very little hope that we're going to have a secure computing device in the next 20 years. I have strong hope that we can have secure systems by just diversifying a little bit. Like the security between having an iOS and an Android device on a multi-sig wallet is probably better than most big companies have for their OPSEC, like their operational security. It's probably better than a lot of big companies.
Conceptually, I think a lot of people get confused with multi-factor authentication
Yeah.
and multi-authorization.
Mm-hmm.
Multi-sig
Yeah.
is a multi-authorization.
Yes. Yeah. Did you have a question?
I was going to ask. Okay, since we're talking about multi-sig,
Mhm.
besides Copay, who the heck is doing this?
I think there are a couple wallets that have tried. I don't know.
I mean,
Excuse my shameless plug, but you should probably be using at least Copay, maybe Bitauth. Just as a general, there's a reason why the team there is so concerned about multi-sig stuff. It's because it really is the only way to keep your money safe right now. If you're holding Bitcoin in the year 2017, you're probably, if Bitcoin gets big, you are still on the cusp of this. There are going to be a lot of big hacks still. I'm waiting for the day that the first hardware wallet gets hacked. But and it's going to be through some weird buffer overflow bug, and it'll be explained away. But and someone will then the next day say that we're going to have hardware security soon. But I don't believe it. What's that?
Long a node and use your own wallet.
I would say if you have some sort of wallet that allows you to have multiple devices that must sign for your money to be spent. The other viable option is if you're technically savvy, setting up a cold storage device, but that is hard, and it's easy to do it wrong. And be sure you rip out the speakers also, not just the Wi-Fi and the USB and the Ethernet and the Bluetooth, because there are active security exploits for those things too. So it's hard to set up cold storage. It's a lot easier to diversify your risk with a multi-signature wallet. So yeah, shameless plug. Copay is probably a good. If you've got more than a Bitcoin, do yourself a favor and do it right. Just write down your 12 words. If it's 36 words total, stick it in your safe. You're probably good. But you don't want to be stuck to these ecosystems because they're not secure right now, and really have no hope of being secure within the next year or so. Right. So we're talking about your security right now, and right now this is pretty bad. So on a high level, we've discussed how these app developers might have identities, which are resolved directly to a big number. They are resolved to a hash of the auth base, right? So we can trace their latest signing stuff. So using the auth base ID, which is it's a key value in Microsoft, is this 30-digit number, right? This is Microsoft. This is BitPay. This is Facebook, Twitter, etc. Right? We can those companies can sign their apps with an auth base, or with an identity derived from an auth base. The app can have its own auth base, which allows us to do some really, really cool stuff. So if what the gentleman in the back mentioned, 12 words for a backup system. Those are called hierarchical deterministic wallets. You take those 12 words, you do some fancy stuff, you generate a private key, and anytime you type those 12 words into a wallet, you type it into another Bitcoin wallet, it'll do the same calculations and come up with the same keys, and all your Bitcoin will be right there. Well, the question that I was trying to solve in 2013 was how do you get the same experience, the same 12-word backup, and have it work across like an entire ecosystem, right? What if every app on your phone could have its own private key associated with the same 12 words, such that you lose your phone in a lake or something, it burns up in a fire. You've got your 12 words, or better yet, for a lot of less technically savvy people, maybe Google has half of your 12 words and Apple has half of the others, right? So there are lots of corporate ways that we can make this easier for less technically savvy people. And your device has these 12 words. Then at an operating system level, every app, given its auth base, can ask the operating system for its set of private keys. Right now, if it does anything with those private keys, if everything goes to hell, it can grab. You can put those 12 words back in the wallet, and it can rederive, back in the next device, and it can rederive your private keys for all of those apps. So here we go. So basically, what you can do is you can take the device seed, your 12 words, and you can have an operating system call on Android, which asks for the app asks for its private key. All it has to do is ask for its private key. the operating system grabs the auth base of the app. So this is the cornerstone of the identity, right? If this is compromised, the whole company's gone, right? And they've done lots of work to keep it secure. The operating system can can use that, and I did this just a little while ago. That's the operating system can use the so for example, for app A, it can use auth base A to do some creative math to derive a new hardened extended private key from your device private key based on that auth base, right? And so now, as the app evolves, as they move developers, as they later in the future, the app has a new signing identity, etc. Whatever. When you re-download the app asks your operating system again for its private key. It gets the exact same thing, right? Because it's based on the same 12 words, based on the same auth base, and it's just verified to the latest auth head, right? So this allows us to have a single device-wide 12-word backup, which restores all of your credentials for all of the apps. If you have Bitcoin or if you have other kinds of digital assets or things like that, this is a fantastic way for this system to, on a high level, secure those things. And I wanted to explain that really well because that is what makes this make a little bit more sense. So the phishing stuff that we talked about earlier, this is the last slide. Thanks for sticking with me. The phishing stuff we talked about earlier. Phishing is when somebody creates a fake version of Twitter or whatever with 2 T's or 3 T's or whatever, and your grandmother goes and types in her password and clicks log in, and it actually goes to the attacker, and the attacker signs in, and the attacker tries to sell her back a Twitter account or whatever. If they get it by tricking you into believing you're logging into the wrong service. Well, one way to get around that is to never trust users to identify where they are, and one way to do that is what we just saw. Right? If the user, you've got the 12-word backup for a relative who's in another country and you can't talk to for the next 6 months or something, right? They're in the backwoods of somewhere that doesn't have internet. You've got the 12 words, and you can put those 12 words into the device, and basically you could download every single app in the App Store, and all those apps would ask your operating system for the private keys that are basically for those apps. They're only derivable by those apps because the operating system will only give it the private key that's based on its auth base. It must be signed by the identity in order to get that private key. And every single app in your phone can restore any assets that were there. So it allows us to take those 12 words and then without even knowing that your relative had a Bitcoin wallet. With enough processing power, just loads up those apps. The apps ask the operating system to do some derivation, and the wallet says, you have this many Bitcoin, and then you know that was there. Right? So this is a fantastic way to do backups on systems where you don't necessarily know what was being used or how it was being used without breaking that trust model. So it's basically you get these security isolation contexts for each app, where you don't trust any app with the keys of any other app. But so far as you trusted the app before, you can still get your money back, right? So a phishing-proof login will look a little bit like this. You click login, and then you're signed in. There's no reason to do anything else, right? So this would be a fantastic experience, right? It's already hard to type in your password, and it's already useless, so you might as well not. So what we can do instead is we can, basically the service has an auth-base ID. The service, in a message to you, sends a login challenge, which is signed by its auth-base ID, signed by the right auth-base. And you don't even have to check that it's signed by the right auth-base, mind you. All you need to do is check that it's signed that the message that it sent you is signed by the auth-base that the message claims to be, right? So that's all you have to do. Then you use your 12 words that we saw in this last slide. This guy you use the device seed or whatever, or in the case of Chrome, if this is a Chrome extension, you use the 12 words that are built into the Chrome extension, and you derive a new key using the service's auth base. As long as you do it the same way every time. Here I gave it as an example. I hash it. There's no reason to do that, actually. I was just not thinking clearly when I put that up there. So you can basically, I've got this function, derive key, based on the service's auth base. You take the auth base, which is the signed message, you know that the auth base that signed the message asked you to log in. You can know definitively. Now, if you derive the key using the auth base, you've now made it impossible to get phished, right? Because fundamentally, the login challenge was definitely signed by the identity by which you're getting the keys to begin with, right? And it works that way forever. So you take those 12 words, you back it up, and grandma forgets that she ever logged into the site ever. But if you put those 12 words back in the Chrome extension, you go back to the website and click log in, it will be the same auth base. Always. It will be the same identity that gets sent back to the server, same keys, everything. Then you sign the login challenge it sent, and you send it back, and you're good to go, right? And so you've now got a really, really nice password manager. It's a 12-word backup. You just stick it in your safe on your Bitcoin wallet, or maybe it is your Bitcoin wallet, which just works. You just click login, and you're logged in, right? And now what I really wished that I had when I was hacked November 1st was this, phishing-proof multi-factor login. I didn't get phished. It was actually through a mistake of mine in the backup number with Google. Part of the kind of static authentication stuff I was discussing earlier. When you have that many pieces, it's common for people to not necessarily understand how different services are using those pieces. So, by the way, if you have a Google, there's a great article one of the Bitcoin companies put out, but if you have a Google account and you added two-factor authentication, you should go back and check and make sure it didn't add your cell phone number as a backup. Because by default, and I can't fault them for it because it's a business decision, by default, Google puts your phone number as a backup number when you enable two-factor authentication, right? So when you go back and you enable real two-factor authentication with Google Authenticator, it's one-to-one. You scan the QR code, you get 6 numbers, you type it in. It's absolutely rock solid, right? Well, they actually put your phone number as a backup number for the account. So what you might not realize is when you set up two-factor, if you're not being careful, you probably reduce your security because the number. That number, they can just call, the attacker can just call Verizon and convince them you're your mother or something, and convince them that you lost your phone and you need to switch to this new phone, and they will give you the phone number. In most cases, that happens all the time, and about $40 million has been stolen in the past 6 months from people in the Bitcoin space through this problem. Most of it, so far as I understand, is because of that backup number thing. Now, it's a business decision on Google's part because there's also a bunch of people who enable two-factor authentication who don't get the ramifications, don't understand they need to keep the backup codes, can't do it, and then they lose access to their account. Now it's a big support problem for Google, right?
Fundamentally, a cell phone is never going to be used as a second.
Yeah. It's a bad idea to use an SMS number as a second factor. Yeah, so it is a very serious problem right now. But that goes back to the point of that whole static authentication thing. There's a monstrous static authentication system that Google has erected, which is very highly efficient at what it does. Right? They've been working in this world where static authentication is the best you can get. Right? And they've done very, very well at keeping most people's accounts secure. They're doing all sorts of risk analysis, stuff in the background. They're checking the IP address of people coming in. They will send you an email if it looks kind of suspicious. It's all sorts of stuff they do to make their security better. But there are some kinds of decisions that I, as a more security-conscious person, I would not have made the decision to leave a phone number on my Google account if I had realized that that's how it worked. But it's something that just kind of it just does it in the background, and it doesn't really mention it. You have to, when you go back in, you have to click a couple more times to find where it did. Right? So the instant I got hacked, I told all the people that are close to me related to the Bitcoin space to make sure that they don't have a backup number in their account because they probably do. And of course, lots and lots of people have backup numbers because it gets set automatically. So it's one of those things. It's funny. You would think that adding two-factor to your Google account would help. It usually doesn't. Basically, not unless you know how it works. So if you added two-factor, it is helpful. Just make sure you go back in there and remove any backup numbers or phone numbers or emails or anything like that. Only backup codes you should have are written down on a piece of paper and in a safe or something. Right? Anyways, right? This is how we would get around that. This is a fantastic way to avoid that whole scenario. User clicks login. I've enhanced this a little bit because in the last instance, you might have noticed that the last slide I didn't show how would you log in as a different identity, right? If the user has multiple Twitter accounts, the way that I just showed you wouldn't work. But here I just showed I've got a login, and it says then on my computer I picked between two options, and I said Bitjason, me, or if I want to log in as my secret Satoshi identity, I put in parentheses, not really, not Satoshi. And you click on Bitjason or whatever.
You said 2009 you got into Bitcoin?
So you click on Bitjason, and now my Chrome extension or whatever, it broadcasts that the login message. It broadcasts that out to the server that pushes it to my phone and the other 3 devices that I've got on my multi-signature identity, right? So I've got 3 different phones that control my identity. I am super paranoid. I'm totally going to do this. The minute I get the chance to do this, all of my accounts are going to look like this. By the way, yeah, at least 3. So what it does, it's probably hard to read at a distance, but it's going to check the signatures. It's going to check the signature to make sure that this is a recognized browser. Right now, we can have an identity for our browser, and all of our phones can already be paired with a browser. Right. So when I get a message from my browser that says, "Do you want to log in?" My phone can be like, "Do you want to log into Facebook on Chrome on your Mac?" Right, and you don't have to see anything. It just says, "Do you want to log into Facebook on Chrome on your Mac?" You get a push notification. I'll be walking around with 3 phones, right? So I'll have buzz in both pockets and one pocket twice. I'll pull them all out, and I'll swipe them all over and click yes, right? And then it'll broadcast it back to my. Rather, when I clicked yes, it did the derivation thing as before. The accounts, maybe my first account is account 0, the next account is account 1, etc. So this allows us to still restore our backups without necessarily knowing how many accounts we have. Right? You don't need to. This is a password manager that doesn't require constant backups. So identity 0, identity 1, and you send it up to the send it up. They all sign it. They send it back down and send it on to the service. The service recognizes that's the auth base that Jason signed up with us, in the year 2011, and it's 2017, but it can still resolve almost instantly what my latest signing requirements are, and it was these 3 devices, and so it checks it off, and you're good to go. So for the net user experience then is you click login, you click the identity you want to log into. I then my pockets start buzzing all over, and I pull them out and swipe over and click yes. And then the screen switches over, and I'm logged in. Right. So at no point in time did I type anything, which is always the worst part. Typing is when you have phishing problems. So by the way, if you're designing a system and you start typing something, that's the part that gets phished. Just so you know. But yeah. So any questions on how that would work? Does that make kind of intuitive sense? I think it's yeah.
So this requires the services to be in the Bitauth.
Yes, so this lady in the front just mentioned that this would require the services to be able to resolve the auth head from the auth bases. Yes, it would. So big companies running full nodes is probably something you would begin to see quite a bit. And that's cool because it's awesome for Bitcoin, fantastic for Bitcoin. It's a fantastic incentive to run a full node. And I would say that the companies would do this because the Bitcoin blockchain is the world's best identity database, right? So we talked about earlier, is it necessary to spend money to create an identity? A few pennies. It costs you maybe a quarter to create an identity or migrate a transaction. I don't think that in the long term, that will be a problem. I think long term, everybody's going to do that. It'll be a normal thing in regular life, right? A lot of people are into free services right now, so I wouldn't be surprised if there were kind of some off-chain options or some services that pay the fee for you. And so I expect that in the coming years, we'll see a lot of that. But in the distant future, when you've got money on your phone, it's going to be no big deal you're going to regularly pay transaction fees if you do. And if the price of transaction fees on the Bitcoin network goes up, by the way, I'm sure we'll be able to come up with ways of bringing these things onto side chains and things like that. Right? So the same scaling problems that are true for Bitcoin are just the exact same scaling problems that are going to be true for an identity database that's shared between Twitter and Google and a bunch of companies like that. Right? Those companies would be crazy to not use the Bitcoin blockchain because Bitcoin has been running for 9 years. It's rock solid technology. It's got a $13 billion bounty on it, right? if anybody could get to it, it would have been done, or it will be done, right? So it's like The Bitcoin blockchain is already a fantastic directory of identities, and it would be kind of crazy for a company to not use it for that purpose, right? So, as you mentioned, the auth-head resolution is possible. It's possible using SPV validation, simple payment verification. You can run a very, very small Bitcoin node on a very underpowered device or a relatively underpowered device, and it can do most of the validation it needs to do. The only validation it really needs to do is to get the headers of the Bitcoin blockchain. Right now it's like 100 megabytes. So it sounds like quite a bit, but relative to data storage now, I mean, it's like $4 for 2 terabytes or something on Amazon Glacier, right? So relative to data storage, that just doesn't matter at all. And if you want, there's actually ways of reducing even that requirement. But fundamentally, you can run the you can run a small little node on a phone and have it do the same extent of validation that you would do on any big computer, right? Now, as a service, you're probably going to want to run a full Bitcoin node, because the only way you're going to get zero latency validation is if you already have all that stuff cached. So if you have a full copy of the Bitcoin blockchain, you can reduce your login times to below 1 millisecond and stuff like that. So for a phone, they're going to run SPV validation. It's going to take like 3 or 4 seconds or something. If Google provides the proper proofs, it sends it down to the phone, and the phone checks against a couple other big companies. I'm sure that process can be brought down to a few seconds. When you're talking about login and authentication with Facebook or Google or something like that, they're probably going to be running Bitcoin nodes at their edges. They're going to be running it as close to the user as possible, and they're going to have cached versions of basically auth-head resolutions, right? Every Bitcoin transaction on the entire chain ends up at some sort of auth-head. So you can crush the entire blockchain down to a list of key values. That this is the auth base, this is the latest identity. And you can turn that operation into a 2-operation task if you're running a full node. So the final conclusion that I'd say, the final implication of this stuff is that there's a good chance that if we're able to get it working nicely, we provide the right ecosystem, we get the ecosystem developed, we could see in the next few years, maybe 10 years or so, I should probably be more conservative. In 10 years, we might see a lot of big companies running Bitcoin nodes, and they're gonna like it because right now they are dumping money into static authentication systems, which are leaky and still don't work. They still have massive calamitous effects on all sorts of different problems, as we've seen, and we just discussed a few minutes ago about 40 million. Forbes published an article in December, which is where I'm getting that number from. About $40 million has been stolen in the past 3 or 4 months via basically that number backup thing. That we discussed, right? So the people who thought they had two-factor, but they had TOTP two-factor, they had Google Authenticated two-factor, but they didn't realize that there was a backup number on the account. So, so these are very, very real problems, leaky security with static authentication systems, which are on a high level insecure and probably need to be replaced. And I think that these companies are probably going to take a look at a system like this. And once the ecosystem develops to the point where the user experience for this is better than all the work that they've put into it, most of these companies are only able to put a few $1 million into the user experience of their authentication system. And all of them are burning that money across the board, reinventing wheels. So if a few different security companies really pick this up and make that experience better, they'll get to dump all of that work, they'll get to cut off that entire business expense and replace it with just some simple Bitcoin nodes, which are pretty cheap to run. So, should be good.
Is there a bid for this?
There is, and it's at this address, github.com, bitjason, Bitauth2017. And this presentation is bitauth.bitjason.com. You can just search for Bitauth2017 though, and you'll find this definitively. And yeah, thank you.